slope fields. Again, seems strange that we're doing 6-1 last when it would actually come first. But a slope field is basically a partial graph of a derivative that gives us, like it says there, a glimpse of what the original could look like. Okay. Now let's face it, that's what antiderivatives do. It should get you back to the original. If you have the derivative, antiderivative should get you back to the original. And notice that I chose, I kind of have the XY axis on there, and I put a bunch of dots on there. The number of dots you get totally depends on the person giving you the problem or which ones you need. I could give you the dots somewhere nowhere near the origin. You notice here I did. And basically the reason I did that is these are probably going to be the most helpful dots. What we're basically going to do is we're going to put on each one of those dots, we're going to put a little segment that kind of shows what the slope would look like there. And once we fill in all the dots, we should have a pretty good idea of what the original could possibly look like. With one exception, we don't know what the constant is. And so this is basically showing us a bunch of options of what the original could look like, depending on what the constant is. Okay? And so really remember, all that stands for is, yes, it stands for derivative, but it also stands for slope. Change in y over change in x. It's just delta has been written differently. And so to find the slopes at these points, all you have to do is pick the point that you're going to find the slope of and substitute those values in. So for example, let's start with probably the easiest one. We'll start with 0, 0. If I plug in point 0, 0, that means every place I see an x, I'm going to put 0. Every place I see a y, I'm going to put 0. But are there any y's in this derivative? No, so we don't have to worry about it. But there is an x, so right there I'm going to put 0. So if you put 0 there, you take 2 times 0 is, plus 1 is. So the slope here is 1. Do you agree with that? You see how I got 1? So you go over here at 0, 0, and you make a slope of about 1. There's your little segment. That's all you do. But you got to do it for all the points. So let's try this one over here, 1, 0. You don't actually have to write them down if you don't want to, but I'm doing it so you can see it. So if I do 1, 0, that means put 1 in for x and 0 in for y. And so if you do that, what do you get for a slope at 1, 0? Again, you put 1 in, 2 times 1 is, plus 1 is 3. So how should I show that that slope over there is much bigger? Yeah, just make it steeper. Do I need you to sit there and actually measure this thing? No, just obviously that's more than 1, right? It's slope of 3. And so you just keep going along like that and you figure it out. So let's do -1, 0. Again, you don't have to write them all down if you don't want to. And what do we get there? So you put -1 and say -2. So is it -1? Do you agree? Well, how do you show a slope of -1? Yeah, it just kind of goes the other way, right? Okay, we'll do one more together and then I'll set you off on your own. -2, 0 we'll do together. -3, I've been told. Are we in agreement? Once again, you're just going to make that one steeper, depending on how you want to look at it. Does it make sense that it's going to look parabolic? Why? Would that be the derivative of something that was a parabola? Yes, it was. Okay, so go ahead and finish off what that looks like. Just do those points. You should get a pretty good idea of what's going to happen. Every dot is how you have to do slope fields. Fill them all in. Let's face it, most of this you can do in your head. Yes, perhaps looking for a pattern may save you some time. Okay, as some people were working here, they noticed that there's a distinct pattern because there is no y to substitute into this derivative. So your x value is all you're plugging in. So every x value should really end up the same. For example, if I put an x value of 0 in, which would basically be all of them on the y-axis, they're all going to be the same. They're all going to be 1. So it should look pretty much the same. If I put in an x value of 1, which is basically the next slot over, all the slopes better be 3. So you just make it a little steeper. These will all be -1. These will all be -3. And does that kind of look like a parabola? Can you see it in there? Yes, you can. The only reason we have to do them all is we don't know what the constant was in the original. So all of these could be what the original looks like. Maybe it's the one that comes through here and does something like that. Who knows? Depends on the constant. Maybe it's the one that comes down through here and does that. We don't know. Okay, because there are a bunch of points in between that we did not fill in, and we don't know the original's constant. Okay, so this is basically giving us all of them.
Since we don't know the constant, we just pick up these diagonal what comes out. Would they all?
Okay. They won't all have quite this distinctive a pattern, if that's what you're asking, because the next one, there's an x and a y in the derivative, so this probably was done implicitly. If you remember when we took derivatives, and sometimes the y ended up in there. And so this one is going to take a little bit more work. So let's just start with some easy ones again. Notice I gave you slightly different places. Okay, this one's harder for you to see the original. Okay, but I'm glad that somebody realized, hey, isn't that kind of looking like a parabola in that last one? So let's go ahead and try, I don't know, 0, 0. So you put 0, 0, because that's one of the points. So you put 0 in for x, 0 in for y. What's the slope? 1. Don't always think it's going to be 1 at 0, 0. That's not how it necessarily works. What point do you want to try next? -1, 0. So you put -1 in for x, you put 0 in for y, and my slope is 0. How do you do that one? Yeah, horizontal. Probably should have chose a color other than black. All right. So what do you want to do next? If I were you, I would work as a group and maybe have one group do the top row, have another group do that row, work together on this would probably be my suggestion. So perhaps one of you needs to be a leader and kind of distribute who does what. Do that now. Okay, hopefully you took some time to finish those up. Here is what the slope field would look like. Well, on the last one, you could tell me that the original was probably parabolic. Can you tell me anything about this original? What does this original probably have in it? An asymptote. What kind of asymptote? A slant. Very good. The slant asymptote's probably somewhere right in that middle range there. The originals could look something about, based on what you see there, probably something like that. Is there probably a vertical also involved? Probably, right? But very good. It's still going to look something like that. It just might move depending on how far away from the asymptotes it's going to be, is basically all you have to watch out for. Well done. All right. So that's basically day one. What I'm going to do, seeing I am going to be gone tomorrow in this particular instance, is we are going to do this one as well. It's really not that hard as day two. I'll have to write them on the board, but you have them already in your notes. So it's basically saying here is your derivative. And what I want to do is determine all functions that would actually have that as a derivative. Well, how can you figure out all the functions that would have that as a derivative? Yeah, take the antiderivative. What is the antiderivative of that side? Okay. Now, some of these are easy. Now, secant squared, that's not one I expect you to know right off the top of your head, but you do have a sheet of paper that has that for you. Yes. Nope. Just tangent, yep. Now, how come I didn't have to do substitution on that one? Because the angle is just x. No need for substitution there. Any need for substitution for this next part? See, these are all plus, so you don't have to worry about it. It's when it's multiply that you have problems. So basically, it's x squared, yep, because you take it up a power, divide by your new power, the 2's then cancel, right? Plus 5x. Is that every single function that could possibly have that as a derivative up there? It is. There you go. Do you see how that works with the slope field? The slope field showing you all the functions that could be. This is showing you the actual function. All right? So back here on this one, could I have taken the antiderivative of this? That would have been x squared plus x plus a constant. And this is what they would look like. All right? So this is why I put this at the end. It probably makes more sense that you know how to take the antiderivative so you can see it. And your other one is asking for a particular one. So this is saying, okay, the derivative is e to the x minus 6x squared. But it's saying the original has to go through 1, 0. Is this the original that I have written up here right now? No, that's the derivative. Okay. So what we have to do is once again take the antiderivative of both sides. The antiderivative of this side, there you go, equals. You can do them separately. You can do them separately because it's minus. If this was times 6x squared, would be doing the antiderivative this easily. No, if it was times 6x squared, I would go to tabular method to take care of that one. Okay. But this is minus, so you take the antiderivative, it is e to the x minus, well, basically it's 6x to the third over 3, right? Okay. Which does simplify to 2x to the third plus a constant. But now what we have to do, this is asking for just one of the answers. Not all of them, one of them. Where am I going to substitute 1 in? For any place I see, and I'm going to put 0 in any place I see y, and I see a y right there. So 0 equals e to the first minus 2 times 1 to the third plus a constant. Yeah, c is the only variable left because we're finding just one of the answers. Okay, and so we need to know exactly what the constant is. This constant is not all that pretty because obviously if we got to get c all by itself, well, yeah, let's minus e over, so let's just write it as e. And then we're going to add 2, right? You would subtract the e over, you would add the 2 over. Because 1 to the third is 1 times 2, that's why I just moved the 2 over. So my constant is basically 2 minus e. So is there a question? Okay. So your constant you replace with that whole thing because e is a number. And this needs to be an exact answer, not a rounded. So you can't just do 2 minus e on your calculator and round that. That is the exact answer that has this as a derivative and goes through that point. It's the only one that does both of those things. How come I didn't substitute in for the constant here? Because I wanted all the answers that would have secant squared x plus 2x plus 5 as a derivative.